welcome to thedeciphers.org. My name is Cordelia Kataria, and I am a 9-year-old computing explorer and problem solver. I got a 9 in my GCSEs at the age of just 8, and right now I'm doing my A-levels. So we're going to be doing a free A-level revision session, and it's going to be about integration.
Right. Excellent. So I'm Isaac, an experienced maths teacher, helping out with the Deciphers.org and helping deliver these free online revision sessions. And as Cordelia said, we're going to be looking at integration today. How can people interact and take part, Cordelia?
So they can interact by writing something in the chat if they have another way to solve the problem, or they can see how to solve the problem, or
But yeah, so any questions or any different ways to solve the problem, drop it in the chat. We'll be keeping an eye on that, and you can interact with us and ask any questions. Brilliant. So we are going to be looking at integration, but mostly the Year 13 integration. So that's stuff on the A2 side of the course, stuff we study in Year 13, the Year 2 part. So looking at integration by substitution, by parts, reverse chain rule, that sort of thing. So we start off by talking about some useful results that you will hopefully have seen before, and which ones you'll be given in the formula book. So first of all, we'll say that integration is the inverse of differentiation, and we can think of integration as a mathematical tool that allows us to find areas enclosed between curves and coordinates. So that's what integration is used for. But there's lots of uses of integration, and it can be found in other fields of study such as physics, statistics, and economics. So if you're thinking of going on to university to study economics or physics, then you'll definitely be seeing lots of integration there as well. So some useful results that sort of come from what we've looked at from differentiation. And if you haven't watched we did 2 sessions on differentiation, which you can go back and watch on our YouTube channel, which will be helpful. So some useful results that you need to know. So when integrating a polynomial, so if we have x to the n and we integrate it, we raise the power by 1 and divide by the new power, similar to that's what we would have learned in Year 12 on the Year 1 integration topic. If you have e to the ax plus b, then when you integrate that, you'll still have e to the ax plus b, but you divide through by the derivative of the power, which in this case is a constant, so you divide through by a, so it's 1 over a e to the ax plus b. 1 over ax plus b, so if we integrate a fraction with an x on the denominator, that comes from an ln, because we know when we differentiate ln x differentiates to 1 over x, so similar sort of rule. So these two, the e to the x and this rule here, is like a result from the reverse chain rule. So if we have 1 over ax plus b and we integrate that, we have 1 over a divided by 1 over a times by ln of the denominator, ax plus b. If it's ax plus b to the n, again this is an example of the reverse chain rule. We have raise the power by 1, so ax plus b to the power of n plus 1, divide through by the new power, n plus 1, but we also need to divide through by the derivative of the bit in the brackets, which is where the reverse chain rule comes in, which is ax plus b, so we differentiate that and just get a. If we had a polynomial in the brackets, it's a little bit more complicated, and we can't do that. Just that we can do it just because the derivative of the bit in the brackets is a constant, which is why we can apply that reverse chain rule and just divide by a. And then also we differentiate when we're integrating our trig functions sine and cos. It's just like when we differentiate, then we use those results. So sine kx integrates to negative 1 over k cos kx, because cos differentiates to negative sine, so sine integrates to negative cos, and cos kx integrates to 1 over k sine kx, because sine differentiates to cos. Okay, the results that you'll be given in the formula book, but you should still know how to derive them, because you may be asked to prove them. Tan kx integrates to 1 over k ln sec kx, cot kx is 1 over k integrates to 1 over k ln sine kx, cosec kx integrates to negative 1 over k ln cosec kx plus cot kx, sec kx integrates to 1 over k ln sec kx plus tan kx. So you'll be given those results there, these ones, in the formula booklet as they are like that. But also some useful results in the formula booklet are in the differentiation sector. So for example, you are given the derivatives of tan, sec, cot and cosec in the differentiation part of the formula book. So we can use those in reverse to get the integrals of their derivatives. So for example, we know that tan x differentiates to sec squared x. So if we wanted to integrate sec squared kx, we can use that result in reverse, and that integrates to 1 over k tan kx. Similarly, sec kx tan kx integrates to 1 over k sec kx. Cosec squared kx integrates to negative 1 over k cot kx, and cosec kx cot kx integrates to negative 1 over k cosec kx. So they're given it in the differentiation part of the formula book, but they are still given to you in the exam, so you don't need to remember them, but you do need to remember how to derive them, how to prove them, because you could be asked that in a proof question in the exam. Two other useful formulas, if you just scroll down a little bit quickly.
So, yeah, scroll down.
So just up a little bit more, so to the by parts formula. There we go, yeah. But the by parts formula is given in the formula book as well, and we'll do an example of using that, and we'll talk about that in more detail in a second. And then the trapezium rule is technically an integration topic or a numerical methods topic, whichever way you want to think about it. We're not going to look at it in this session, but just a note that that is also given in the formula book, so you don't need to remember it. But we may do another session on numerical methods and include the trapezium rule in there. So the reverse chain rule is a useful technique for integrating some complicated expressions, and we can use these sort of two results, the sort of two forms of it. And the idea is with the reverse chain rule, it's just about spotting that you can use it. So for example, if you have if you're integrating something which is like fx, some function to the power of n, multiplied by the derivative of that function, then that's come from the chain rule. So it's spotting that you're integrating something that would have been the result from the chain rule. So for example, sine to the power of 400x times cos x, if you're integrating that, well, you know that sine differentiates to cos, so sine to the power of n differentiated will be sine to the power of n minus 1x times the derivative of that cos x. So this sine 400x times cos x is actually the result from the chain rule, so we're using the reverse chain rule. So we raise that power by 1, which we can see in the red in the formula that it's fx to the power of n plus 1, and just divide by the new power. So sine to the 400x cos x integrated is sine to the 401x over the new power, 401, and obviously we have that constant of integration there as well, plus c. And another good form of the chain rule, the reverse chain rule to look out for, is if you have something of the form f prime x over f of x, so where the numerator is some multiple of the derivative of the denominator, then that can be integrated using the reverse chain rule, using the fact that ln f of x differentiates to f prime x over f of x. Okay, so when you differentiate something with ln over a function, ln of a function, then that would differentiate to the derivative of the function over the function. So for example, if we had 2x over x squared plus 42, we can see that actually the derivative of x squared plus 42, the denominator, is 2x, which we have on the numerator. So if we're integrating 2x over x squared plus 42, we have ln of x squared plus 42 plus c. So remember that you must adjust any variation in constants. So in example 2 of the first rule there, you can see that we have to multiply our answer by a third, since the differential of x cubed plus 4 to the power of 5 is 3x squared, not just the x squared. So we look out for those constants in there as well that we have to multiply by. And while it's true you don't necessarily need to know the above rules, they make some integrations a lot easier than if you have to apply other rules to them. So they're good to use, and we'll use them in this session. Okay, just scroll down a little bit and we'll talk about the substitution method. So integration by substitution is a really powerful technique that can be used to solve more complex integrals, which might not be solvable using other methods. The idea is that we pick a new variable, which we often call u, and it replaces any existing variables in an attempt to simplify the integral into something that we can then integrate more easily. And that's best illustrated in an example, and we'll start off with an example when we look at some exam questions. But some helpful pointers regarding the substitution method is that you will often be told which substitution to use. If not, because you're not always, then a good rule of thumb is to try whatever is inside the brackets or the square root. So for example, if you're given to integrate x times 3x plus 4, a good choice of substitution would be u equals 3x plus 4. But sometimes a good substitution there would be to integrate, would be to set u to be root 3x plus 4. And you'll see that rule of choosing what's in the square root or the brackets, it doesn't always work, but it's helpful to try if you're unsure what to substitute in. You might also find it difficult to spot the substitution, and that would work in hindsight. So in this case, it's best to simply try a couple of things and see whether they are helpful or not. And if you decide to use a substitution when evaluating an indefinite integral, don't forget to give your answer in terms of the variable you started with. So obviously if you make a substitution, change the x to u's, then remember to put that substitution back in because you're integrating with respect to x originally. And then finally, the last method that we're going to talk about and then get onto the examples is integration by parts. And it's essentially the product rule, but used for integration. So when we want to integrate an expression that is a product of two functions, we use integration by parts. And it's just derived from the product rule for differentiation. So if you're integrating two functions, we're going to set one of the functions, the product of two functions, we're going to set one of those functions to be u, and then the other one to be dv dx or v prime. And we're integrating them both with respect to x. So the result is, we're integrating u times dv dx with respect to x. The result is uv, so you need to integrate dv dx to get v, and we're going to subtract the integral of v du dx. So we set our two functions to be u and dv dx, we differentiate u and integrate dv dx. So we have u and du dx, v and dv dx, which we can then put into the formula. And like I said, this formula is given in the formula book, so you don't need to remember it. And then we can also apply the same formula if we're using limits too. So when we're using this method, we need to pick one of the functions to be dv dx and the other to be u. The choice is crucial and should be made based on this rule here. You might have seen this before, it's called the late rule. So depending on which things are easier to integrate. So starting with the late rule, so logarithms, algebra, trig, then exponentials. So whichever function in your expression is easier to integrate, it should be selected as dv dx. Okay, so once you have made the choice, you can proceed to using the formula. So here are some key points to keep in mind when integrating by parts. With some questions, you may apply the by parts formula more than once to get the final answer. An example of this would be if you were asked to evaluate the integral of x squared times e to the x, you need to use by parts twice. And then when evaluating the integral of ln x dx in particular, you get asked this to do by parts quite a lot in exams. If you don't remember the result of the integral of ln x dx straight away, then you have to use by parts. You do so by letting dv dx just equal 1, u equal ln x, and then you can use by parts to integrate. Brilliant. So, unless you've got anything to add there, Cordelia, should we get started on the questions?
Yeah. I think so. Wait, what? Random order.
That's question 1 yet. So first question, a 7-marker. So quite a lot of marks for just one question that is just show that the integral between 2 and 0 of 2x times root x plus 2 dx equals 32 over 15 times 2 plus root 2. So definite integral question. Doesn't tell you what method to use. Like I said, sometimes they will, sometimes they won't. So it's good to know which method to use.
Yep, so I think it looks like either substitution or by parts. So I think we can use, if we do substitution, then
Good choice, yeah. You're exactly right that you can use either, which is why it's a good question. And a lot of the time when you have the product of two functions, like we do here, 2x times root x plus 2, then by parts is a good way to go. But I think because it's just algebraic, there's no trig or logs or anything in there, actually substitution's a more suitable approach. It makes the integration a little bit easier.
Yep, so then if we set u to be x plus 2, then
Okay.
then it would be and it'd be the integral from 0 to 2 off is 2x root u dx. So then we can then it would be 2. So then that is the integral from 0 to 2 of 2 times u minus 2 root u dx.
Good, yeah. So a good technique there is so you've written down the substitution, which is really good. So u equals x plus 2. I always would then just write down what x is in terms of u as well, because it's likely that you're going to make that substitution as well, which you have done in this case. So that's sort of the first thing I do when doing integration by substitution is to write down the substitution I'm doing, so u equals the function of x. Then I rearrange it normally to get x as the subject, but there's also one other thing that we need to do to it as well.
Yep. Okay, so we've gone in terms of u, so I think then we need to change the dx to du. So we just need to do the derivative of u divided by derivative of x times the derivative of x. That is the derivative of u. So and the derivative of that is just du, and the derivative of u is 1. So it's just then the x is the same as du. So
yeah.
So
it's always good to differentiate it as well. So once you've written down u as a function of x, it's good to write down x as a function of u and to actually write down what du dx is, which in this case is just 1.
Yeah, so then I think we need to change the limits to think 2 to 4. So then
Brilliant, yeah, so fantastic. So the limits are values of x,
yep.
2 and 0, they're values of x, not values of u. So because we've changed the variable to u, we need to make sure that our limits change. Well, we want to integrate with respect to u. So, and u is 2 more than x, it's x plus 2. So when x is 2, u is 4. When x is 0, u is 2.
Yep. So then it's from 2 to 4. So then I think we can expand that out. Like,
Yeah, now that it's just root of a single term, we can expand.
yep. So that would be 2u root u minus 4 root u.
du.
And that is du, and that is the same as integral from 2 to 4 of 2 u to the power of 3 into minus 4 u to the power of a half.
Amazing, yeah.
So then I think we can easily evaluate the integrals. So
Don't forget du on that end of that line.
So then it would just be, so the integral of that, integral of 2u to the power of 3 into, well that's 2u to the power of 5 into divided by 5 into, which is 2 power of 5 into divided by 5, and that's 4u to the power of 5 into divided by 5.
Good, yeah.
And
So raise the power by 1, divide through by the new power. Exactly right, well done.
yeah, and then we need to take away then the integral of 4u to the power of a half. So then that's 8u to the power of 3 into divided by 3.
Yeah.
So then that, and then from 2 to 4.
Do we need a plus c if we're integrating?
So then
Do we need it?
Actually no, because the plus c's cancel each other out when it's between 2 and 4.
Exactly, yeah. We only apply that to indefinite integrals.
So then if we evaluate it on 4, we get 4 times 4 to the power of 5 into divided by 4 times 4, not u, minus 8 times 4 to the power of 3 into divided by 3.
Good stuff, yeah. Sorry.
That take away, it evaluated at 2, so 4 2 to the power 5 into minus 8 2 to 3 into divided by 3. Wait, no. That divided by 5 and that divided by 3. And then that is 4 to the power of 5 into is that's 32, and 32
Yes.
times 4 is 128, so then
yeah.
128 divided by 5 and 8 times 4 to the power of 3 into. So that's 2. That's 8 times 8, which is 64, minus 64 and 3. And then just minus, and then that's 4. That's 16 root 2 over 5 minus, then 2 root 2 over 3. No, 16 root 2 over 3, I think.
Yeah.
So then that would be so I think so.
Maybe we could change them all to over 15. Might make it a bit easier.
Yes. I guess so. So then let's multiply that by 3. It's 300 and it's 300 and 4. No, not 4. And 84 divided by
384, yeah.
Minus.
Divided by 15, remember? Divided by 15.
Yeah, 15. And then 64 times 5 is 320 divided by 15.
Mm-hmm.
And take away 16 times 3 is 48. So 48 root 2 over 5.
Good stuff, yeah. 15 over 15.
15. And then 5 times 16 is 80 root 2. And then 82 over 15. So that is 64 over 15 minus plus.
Yeah.
Plus, and that would be 32 root 2 divided by 15.
Excellent.
And then that is and then 64 plus, and then which is 64 plus 32 root 2 over 15, I think. And that's
Yeah, if you look at the answer that to show that question, look at the form of the answer we've basically got there. You can see that you got it right. There's just one thing you need to do to finish it off.
And then the form is 32 and 15 times 2 plus root 2. So we need to factor out 32 and 15. And that is 2 plus root 2. and we'll solve the question.
Fantastic. Let's go straight on to question 2. Yeah, but spot on. That's really good working out there, because it showed you steps all the way, exactly what the examiner would want to see. So well done there.
Then
So question 2, there's 2 parts of this one. There's another 7 marker, 4 and 3 parts each. So given that k, what does that mean? K is an element of z plus. What does that mean?
that means that k is a positive real number. So yes.
Not quite. You're right with the positive bit, but z's not real numbers. It's subset of real numbers.
I think it's natural numbers.
Yeah, this is actually the same as saying that it's a natural number. In fact, saying k is an element of z plus, but z is integers. So n is natural numbers, but when it's z plus, it's actually the same as saying that it's a natural number.
It's the same.
So first part, show that the integral between 3k and k of 2 over 3x minus k dx is independent of k.
So then I think so the integral of 1 over is ln, so then it would be so the integral from k to 3k of 2 divided by 3x minus k, so that dx, so that is I think it's 2 times then 3, I think 3, no, not 3, a third ln of so a third ln of x minus of x, think minus 3x minus
Well, you mean 3x minus k, yeah. Yeah, so yeah, well then it's spotting that it's the inverse chain rule, so which is what we're using here. So it's noticing that actually we know that the derivative of ln 3x minus k would be 3 over 3x minus k. So we're recognising that we've got that derivative. We know that, we should be able to spot that straight away. So we use that in reverse. Well, we don't have the 3 there, we have a 2 instead, so it must be 2 times 1/3 of that. So that's what we're doing, yeah. So we're done.
Yep, so then that is the same as, and if we sub in x as k, then it would be 2 times a third ln of...
Should we just do it as 2/3 rather than 2 times 1/3?
Yep. Of 2/3 ln of 3k minus k.
Wouldn't it be... Well, why are you just putting k in? Shouldn't you need to put 3k in first?
Oh yeah, so 9k minus k. 2/3 of that minus 2/3 of 2/3 of ln of 3k minus k, which is 2/3 ln 8k minus 2/3 ln 2k. So then
it doesn't look independent of k at the moment because we've got k in it. So what do we need to do next?
I think we need to do which is 2/3 times ln 8k minus ln 2k.
Good.
And then I think that's 2/3 times and off and off 8k off that.
Excellent. Good, yeah.
Which
So using our laws of logarithms, yeah.
Yep, so which is 2/3 ln 4.
2/3 ln 4, so it is independent. Okay, yeah, spot on.
Yep. So then, we can move.
That's it, yeah.
Yep. Then you think we
Brilliant.
can do
Okay.
part B?
Part B, yeah. So part B show that very similar integral, but this time it's the integral between 2k and k of 2 over 2x minus k squared. A little bit tricky this time. Integrating that, and we're showing that it is inversely proportional to k this time. So not independent of k, but inversely proportional. So what do we expect the answer to look like? What's it if it's inversely proportional to k?
The answer will look like a constant divided by a constant divided by k.
Yeah, brilliant. Yeah, exactly.
Then in this case, so I think we can do. That's 2 over 2. That's k squared, and then I think we can
So what are your thoughts for this one?
maybe we can just I think we can use the reverse triangle.
You can, yeah.
And so then that is and then that is 2 times, and then 1 over something is just ln and off, and it's ln of 2x minus k squared, and then the derivative of that is
Okay. Yeah, let's just think of the derivative. Because if you think of that, of what there though, if you're differentiating ln of 2x minus k squared, then that's gonna what's that gonna have on the numerator when you differentiate it?
I think that's going to
So what would that look like if we differentiate that?
that derivative is
So it would have the 2x minus k on the bottom, 2x minus k squared on the bottom, but what would it have on the top? The thing with the chain rule, if you're differentiating ln of blah squared, it's going to be 1 over blah squared times by the derivative of blah. So what's the derivative of 2x minus k squared?
So that is that's 4. That's 8x minus 4k.
You're right. Sorry, it is. Yeah, it's 4 there. Yeah, 8x minus 4k. Yeah. But it's a function of x, isn't it? So if we had our original thing that we're integrating was a function of x, maybe we could use the reverse chain rule using ln, but it's not actually an ln, this one. It looks like it's going to be, but because of that x squared in there, it's not. So it might be easier to think of, and the fact it's only 3 marks is a bit of a giveaway, but it's not an ln as well. It's actually easier. It might be easier to think of it as 2 times 2x minus k to the negative 2. That might be a little bit easier to think about it that way.
So so if we do that, then so then it's just which is it's negative 8 and by 2x minus k 2x minus k to the power of negative 1.
Well, you're really close, but think about you're integrating. So I think you've times by the power and by the derivative of 2x minus k and drop the power and increase the power by 1. But if you're integrating, you're right to increase the power by 1 so that it should be negative 1. But you need to divide by the new power, so it is negative still, but you're dividing by the derivative of 2x minus k, not timesing.
So then and it's 2. Then that's just 2 divided by 2 is just 1, so it's just, I think it's just
Just that? Yeah, but let's do a quick check. So if I was to differentiate 2x minus k to the negative 1, then I would differentiate it. So I would times by the power, which would be negative, drop the power by 1, which is negative 2, and times through by the derivative of the bit in the bracket, so times through by 2. So it's negative 2x minus k to the negative 2. So you're close, you're definitely close, but you've put the negative in there now, yeah. First one, well done. So 2 times 2x minus k to the power of negative 2 integrates to negative 2x minus k to the negative 1. Yeah.
Yeah.
So you
No.
raise the power by 1, divided by the new power, and divided by the derivative of the bit in the brackets.
Yep.
That's exactly right.
Now we need to do between k and 2k, which is
Yep.
that is negative 2k minus k of negative 1 minus negative 4k minus k of negative 1, which is negative 1 in k.
Yeah.
Which is minus negative 1 in 3k, and that's minus 3 in 3k minus negative 1 in 3k.
I think you need to be careful because you've put your k in first, haven't you? Rather than the 2k in first.
Yeah, so that's 3k, that's just k, and then
Yeah, it's easy to fix, so you just think about which ones you need to change from negative to positive.
yeah, and then that is 3
So is it?
k, that's just k, and then that's just 1. So that minus 1 in 3k, so that is which is 2 divided by 3k, and inverse proportion is a constant divided by k.
But yeah, so you show that, yeah, basically you can just say that this is proportionate to 1 over k. So you've done it.
So then, yeah, I think we're done.
Exactly. Fantastic. Okay, so question 3. So we've done a substitution, we've done a couple of reverse chain rule. What do you think the next question is going to be about?
Maybe integration by parts.
More than likely, and tying in a bit of areas as well. So 10 markers, this one's a tricky one. Hopefully we'll have time for the challenge question as well. We've got figure 2, shows a sketch of part of the curve C with equation x, l and x, where x is bigger than 0. The line L is the normal to the curve, the normal to C at the point EE. The region shown shaded in figure 2 is bounded by the curve C, the line x. The line C and the x-axis show that the exact area of R is AE squared plus B, where A and B are rational numbers to be found. So first of all, think about what how you're going to find those areas. What are you going to do? Probably a good place to start. Before you even think about doing what we need to integrate.
So you need to integrate. Integrate x as x.
But before you even think about what we need to integrate, I think it's good to think about how you're going to find the area of that shape, because it's not just going to be a straightforward integration question. There's some other stuff you need to think about.
Okay, so Okay, so I think what we can do is just find the integral of this curve from here to here, but then that would then no, from here to here, and then find the integral of the line from this point to this point.
Yeah, brilliant. Yeah. So the idea is, so I'm just going to go with that, is to cut it up into two. So vertical line there, that's E. So you've got a triangle and the bit under the curve, which we're going to use integration for. So I'm going to call this bit here R1 and this bit here R2. Okay, so R2 is just a triangle. So before we think about integration, let's think about how we're going to find the area of that triangle. So we've got the height of the triangle.
Yeah. So
what do you think we need?
And so we need the width.
Good, yeah. So we're going to need to find this point here, where it cuts the x-axis.
Yeah, and then just take away, and then we'll take away that from E. So then it's just, but to find that we'll have to, I think we need to work out the equation of the line to work out
We do.
that point.
So this is why I said it's probably best not to think about the integration just yet, because there's still quite a bit of work to do. It's 10 marks. So let's it's good technique to just think about what you break it down into what you need to work out. So yes, we've got two shapes we're going to find the area of. Okay, one's a triangle. Let's deal with that first before we even start thinking about the integration. So you're right, we're going to find the equation of that line so we can find the width of that triangle, the base of that triangle.
Yeah. Right, so then then to I think we might need to work out E, but I'm not sure about that. Because then we'll know because then we'll know what then we'll know the coordinates of that point, so we can work out then we can do the derivative of the curve and then find the derivative at that point, and then that will help us get the normal.
You're right, yeah. So we've got the only thing we know about that line is that it's the normal and we've got a point on it. So we're going to have to use the fact that it's a normal to that curve, so we're going to have to differentiate that curve. So that's going to be the first thing we're going to do now.
And so y is x ln x. So y is x ln x. So dy over dx. That would be, and so I think we need to use the product rule. So it's x times, and the derivative of ln x is I think 1 in x.
Good stuff, yeah.
And then that plus, and the derivative of x is 1, and ln x is just ln x.
Yeah,
So that is 1 plus ln x. I guess that's the derivative.
Good. So can we now find the gradient of the tangent? Let's call it mt. So that's m with a subscript t.
Yeah. So then it's just that would just be 1 plus ln of e. So 1 plus ln e is the gradient. So then
Yeah, what is ln e?
it's the gradient of tangent.
It's the gradient of the tangent, yes. That's why I said let's just call it mt. So like mt.
Yeah.
But what is ln? What does ln e? What's the value of ln e?
And that's just 1 because it's e comma e. So then e is 1. 1
Yeah,
plus
so
1 is 2.
Yeah.
So, and then for the normal, it's just minus 1 divided by 2.
Let's call that. Yeah, let's call that n.
Yeah.
The normal.
Divided by 8. So then that's minus 1 and 2. And then 4. And then so it would be y is minus 1 and 2 x plus c. And if we do...
Yeah, I think rather than doing that form, because it's going to be easy to use y minus y1 equals mx minus x1, because then we don't really need to find the plus c with what we need to, with what we're doing, because we're finding the where it crosses the x-axis.
So then it would be so y minus and then y1 and so
Remember we put the point e in there,
yeah.
so x1 and y1 are both e. Yeah, y minus e
equals to m times
m's negative a half, remember?
Yeah. So minus a half times by x minus e.
Good. And we don't need to do anything else with that at the moment. We don't need to rearrange it or simplify it, because actually what value are we trying to find?
We're trying to find we're trying to find we're trying to find the point when y is 0.
Yeah, so we put that in straight away. So that's why I said that y minus y1 equals mx minus x1 is easier, because you don't need to bother with the plus c, you don't even need to rearrange that. You can plug in y equals 0 straight away now.
Yeah. So y is 0. Minus e is minus a half times x minus e.
Yeah.
So that's...
I would here just times everything by something. What do you think I'd times everything by?
By -1, so...
Or not, I'd even better than -1?
-2, because then that would make the make it just delete that constant.
Yeah, it'll get rid of that fraction, get rid of that. So yeah, times only by -2.
So then 2e is x minus e. 3e is x. So that's
it.
0.3e.
Okay, so you were going to you're right. Yeah, so the base is 2e, so now we can find the area of that triangle nice and easily.
So it's just half times by the height and the width, which is half e times 2e, which is e squared.
Brilliant, yeah, and that's R2, isn't it? So let's put that R2. Right, so we've done the bit, we haven't actually used any integration yet. Good differentiation there, so good bit of revision of product rule and differentiating logs. And some coordinate geometry, but now we need to find the area of R1 to add it on. So let's write down R1 equals which integral?
Right. R1 is the integral of x ln x between I think between that point and e.
Good. So we know the upper limit is e. How are we going to find that other point where the curve crosses the x-axis?
Let's do it. We can just set that to 0. So x ln x is 0. X is so either x is 0 or ln x is 0.
Yeah.
So then if we do e to the power of this, then x equals 1.
Yeah, x is 1. Yeah, ln of 1 is 0. So we're integrating, so R1 is the integral of x ln x between e and 1.
Yeah, so when then if we then I think we need to integrate then, so then we need to use integration by parts, because that's multiple of two, that's two functions multiplied together. Also
Brilliant.
dx. So
Yeah, brilliant. And so we need to set one as u and one as dv dx. And which one do you think we're going to set as x and which one as u and which one as dv dx?
Well, so the one that's easier to integrate. One that's easier to integrate is the x. So we're going to set dv dx is x, and u is ln x.
Good stuff, yeah. And as well, what's nice about not only is dv dx x is the easier one to integrate, but also ln x is nice to differentiate, especially when you're multiplying by some function of x, because it cancels things down nicely.
Yeah.
So we integrate dv dx and differentiate u.
Yep. So then v would be x squared in 2, and du dx is, and that is the derivative of ln is 1 in x. So if we use the by parts formula, then
Yeah, which I've just written down for you. It's given in the formula book, so.
right, that is integral of u dv in dx is, wait, actually I think we can just begin subbing it in.
Yeah, we can sub things in. I've written the formula down, so you don't need to write it down again.
Yep, so then it's ln x times then dv in dx is x ln x dx is, and then uv is, wait a second, so uv is ln x times x squared and 2. So,
Yeah.
and then that minus integral of v x squared and 2 times du in dx, which is 1 in x, dx, and then that is x squared in x squared times ln x in,
Yeah, could we write it as a half of x squared ln x? It looks a bit nicer.
so, and then that's x squared in 2 and then x minus that's just x in minus the integral of x into dx, which is x squared into ln x minus, and then that is x squared minus x squared in 4 . So
Yeah. So,
and then we just need to find the area between 1 and e, and
yeah.
also the plus c, but because that was the indefinite one, now we're doing so x squared into ln x minus x squared in 4 between 1 and e.
Mhm.
So that is e squared into ln e, but ln e is just 1, so e squared into minus e squared in 4, and then for 1 it's a half ln 1, which is 0.
Good stuff, yeah.
Oops. Half ln 1.
So because it's a show that, because I know you're rubbing it out as you go along, but in an actual exam, it's good to show those substitutions a little bit more explicitly. So, it probably would be best in your exam to write down that you've got ln e in one step and ln 1 in the other, even though you've cancelled ln e down to 1 and ln 1 down to 0. But yeah, it's good to show the substitutions just in, just so it's clear to the examiner that you are making it, particularly with the showing question.
1 second. 100%. Draw. Wait a second. Microsoft. 1 second. Where is that? Microsoft. It's just Microsoft when it's just like got kind of.
It's right. It's like frozen.
The Microsoft when it just got like disconnected from OBS or something. I'm just.
I think it's still showing. It's still showing on the stream.
Yeah. Like, do you see that thing?
I just did the same thing. I can see it, but it hasn't come up on the stream yet. But there might be a bit of a lag. I don't know. Maybe OneNote's not updating on the stream. You're moving on the stream on the video. I can see me and you are still live, but the OneNote's not.
I'm going to stop streaming a bit.
We'll fix it.
We fixed the issue. Okay, let's
hopefully it's all working again now. Yeah, it looks like it is. Good. So, you subbed in E, and I was just saying that you subbed in E, x squared over 2 ln E is just x squared over 2, so E squared over 2 minus x squared over 4 becomes E squared over 4, and you're taking away when you substitute 1 in, so a half ln 1 minus
half ln 1, and that minus 1 squared over 4.
Yeah.
So then that is E squared over 4 minus just 1 squared over 4, which is just 1 over 4.
Fantastic. Remember, this is all we're working out here is the area to R1.
Yeah, so then that is a quarter E squared minus a quarter. So
fantastic. And then our total area, can we write down R equals R1 plus R2?
So R is R1 plus R2. And R2 is E squared. E squared plus a quarter E squared minus a quarter. So that's 5/4 E squared minus a quarter. And there. So A is 5/4. B is -1/4. And
that's it.
Is
it -1/4? I think we should just go back, have a little look, a few steps back there, Cordelia, because you've got E squared minus a quarter, but then we'll just double check the -1/4 bit.
Okay, so minus x minus 4.
So have a look here.
So it's double negative, so then that turns into a positive, so it's plus a quarter.
It is plus a quarter, yeah.
Okay, then we've solved the question.
Fantastic. Good. That was good. 10 mark question. Normally it would be sort of one of the last questions on an A2 paper. It involves a lot: differentiation, coordinate geometry, and then integration, area under a curve and integration by parts, and obviously lots of logs and exponentials in there as well. So a really good all-round question, a good one to finish up on. So we hope that people watching enjoy the stream, and if you have anything, any topics you want us to cover in future videos, then just drop us a message on the deciphers.org.
Thanks for watching, and remember to like and subscribe. Now let's stop streaming.
See you next time.